Alright, so this is lesson 5.7. Our learning intention is still to derive and integrate a variety of functions. Specifically to 5.7, we're going to integrate inverse trig functions. And so to do that, we're going to need page 4 of our math Bible, which I have for us right here. And notice there we're dealing with the integration formulas. So I have two sets. Notice I have the antiderivative of this is inverse sine. And then I have the antiderivative of this is inverse sine. So this one is more usable and will help us more than these three will, more than these three, because on these three up here you have to have a 1 here. The three that are down here you can have a number instead of a, and use this whenever this number is not just a 1. So this is a little better application to use these formulas than to use these three up here. Alright, so getting started with our first example, and actually before we can do examples for 5.7, we need to review how to complete the square. So I have 3 examples on completing the square, which you first learn in Algebra 2, but we'll review just a little bit before we head into our calculus examples. So to complete the square on a trinomial like this, you want to first of all understand that the whole purpose in completing the square is to get a binomial squared. We want to get something that looks like this. We use it a lot when we're trying to write equations of circles, or when we're trying to transform parabolas into vertex form. So imagine you had this parabola and you wanted to change it to vertex form. So if this were a parabola, it would look like this. And it does not factor in the current format. There's nothing that will multiply to give you 1 and add to give you 4. So we're going to complete the square by kind of taking this -1 and moving it out of the way. So if I move the -1 out of the way, and the process of completing the square basically means this, if you remember using the box, x times x would give me the x squared. The 4x would split evenly amongst these two and become a 2x, and that means you would need a 2 here and a 2 here, which would give you a 4. The question is, how can you get this 4 without having to draw the box every time? Well, all you got to do is take this number and cut it in half, which is what we did when we put them here. Okay? And then you take that number and you multiply it times itself. So you square it. So I just take half of this number and square it to figure out the rest of this square. That's why it's called completing the square. So half of 4 is 2, and 2 squared is 4. So I'm going to add a 4 in here so that I can complete the square. And of course, if you're going to add a 4, and we'll put these in a different color because we added them in. So if you're going to add 4, you're going to have to subtract 4 to make that actually not change the value of the quadratic. So I'm adding and subtracting a 4 in from what I originally had. Alright, well, this thing right here will factor. Clearly you can see it's in this box right here. Here's the x squared, the 4x is these two, then here's the 4, and if you were to factor that, you would get x plus 2 times x plus 2. So this quantity right here is the same thing as saying x plus 2 squared. And then out here, I have a -5. And so we just completed the square. Once again, in Algebra 2, you took parabolas and turned them into vertex form. You went from standard form to vertex form. The vertex would have been at -2, +5. Alright, let's do another one. Let's say we have this quadratic, and, if you were thinking back to Algebra 2, you'd try to put it into vertex form. So anytime you're going to complete the square, you're going to need your x squared term to be a 1, your coefficient. You want your coefficient to be a 1 on your x squared, so we're just going to factor out a 2. And then we're going to leave some room to complete the square. And once again, we're trying to avoid having to draw that box every time, so all I need to do to avoid drawing that box is cut this in half, because that would give me my 2 corners. Half of 5 is 2.5 or 5 halves. So I cut this in half, so that's 5 halves. And if I square that, I square the 5 halves, I will get 25/4. So I want to add in a 25/4. But remember, if you're going to add 25/4, you also need to subtract 25/4 so that you don't actually change the value of this quadratic. So here's what I had to begin with. Factored a 2 out. Now I'm in the process of completing my square. So you cut this in half, that's 5/2. You square that value, that's 25/4. So you add it, and then you subtract it to counteract the fact that you added it. All right, well, now this is what's going to factor for me. I'm going to want to get this outside the parentheses. So if I want to put this outside the parentheses, remember it's really multiplied times a2. So to write that thing outside the parentheses, you're going to want to take this times a2. So if you take the 2 and the 4 and cancel them, the 2 would go into the 4 2 times, and I end up with minus 25/2. And now this part cancels, or no, I'm sorry, it doesn't cancel, that will factor. So that will factor down to x minus 5/2 times x minus 5/2. This number is always this one cut in half. And that's just the box thing. If you were to put this in a box and factor it, this is what you would get. So minus 25/2. So if this is a parabola, then my vertex for this parabola is at 5/2, comma 25/2. Here's another one. If we take this quadratic, notice the x squared is negative, and in order to complete the square, you cannot have a negative on your x squared. So I am going to reverse the order on those. And then I'm going to factor a negative out, but I'm only going to factor the negative out of the first two. And then I'm just going to leave the 8 out here kind of by itself, because I can't factor it in this form anyway. There's nothing that multiplies to give me 8 and adds to give me 3. But now inside of that thing, I can complete the square. So what's half of 3? Well, that would be 3/2. Square that, and I get 9/4. So I'm going to add a 9/4. I'm going to add a 9/4 and subtract a 9/4, leaving that 8 out there, so that I can actually complete the square. Alright, so in order to factor, I'm going to need to get this 9/4 out of there, because the only thing that will factor is this thing right here. So that negative 9/4 is multiplied times a negative 1, which puts a positive 9/4 out here that can be added to that 8. And if you write 8 in terms of force, it would be 32/4. Alright, so now I'm ready to factor. And once again, you could use a box to factor this, but you'll end up with x plus whatever half of this is, which is a 3/2 squared. And now if I add these two together, I get 32 plus 9, which, whoops, you know what, I messed a sign up here, I just noticed. Right here I had a negative. Right here this was a negative 9/4. And when I went down here, oh no, I did it, okay, I took this times a negative and moved it out here and made a positive. Okay, we're good there. So 32 plus 9 is 41, so I have a plus 41/2 force. And that's just simply a review of how to complete the square before we start into these examples. And you don't have to complete the square on all these examples, but on several of them it's quite helpful. Alright, so here's our first example. And if you look back at your inverse trig formulas from your math Bible, notice they're in this form. This one has a square root with two things squared. This one does not have a square root. This one has a square root with a whatever you have here being out here. And u would be your variable in this case, like the x. The a's are going to be constants. So keep in mind the a's are constants, the u's are variables. So if I try to make this one look something like that one, I could think about this 1 as if it were a 1 squared, because that's still 1. And 9x squared I can think about as 3x quantity squared. So now the nice thing about that is if you look back at your formulas, that looks like this one right here. Okay, so the integral for 1 over a squared plus u squared is 1 over a inverse tangent u over a. 1 over a inverse tangent u over a. Alright, so I have a 12. That 12 you're going to think about as coming out front. You do have something that's more complicated than just a u. So your a is going to equal 1, and your u is going to be a 3x. I should probably write those over here. A equals 1, u equals 3x, and of course that means that the derivative of u with respect to x would be a 3. And so if I multiply both sides times a dx and then divide by 3, I'll have 1/3 du equaling dx. So now if I substitute those numbers in, I'm going to bring this 12 out front. I'm going to put in the place of dx, I'm going to put 1/3 du. So instead of this, I'll put a 1/3 du. Well, you can pull that 1/3 out here, and that would be a 3 underneath the 12. And then I will have either a 1 on top, or you could just put the du on top. So now I have, instead of a squared, I have a 1 squared plus u squared. And so now that looks like my formula that I have on page 4, so I can actually integrate that. So remember, your formula is 1 over a, our a is a 1, inverse tangent of u, our u is a 3x, over a, which is a 1, and then a plus c. So when I integrate this, the 12 over 3 is going to become a 4. Remember that I had a 1 over a, my a is a 1, and then I had an inverse tangent of u, which is a 3x, over 1 plus c. And so if I simplify that, that's 4 inverse tangent of 3x plus c. Alright, example 2. Alright, so in this example, notice it has this x out front, and I believe we did have one formula that had an x out front, but I don't know that that will come in necessary here, because if you remember right, the derivative of ln x is 1 over x. So maybe it would be helpful to let obviously my a value right here, once again, that can be a 1 squared. So I believe my a will probably just be a 1 this time, again. My u, let's say that u is ln x. That means the derivative of u with respect to x would be 1 over x, if you remember the derivative of ln. And so now du would equal 1 over x dx. So if I rewrite this as 1 over the square root of 1 squared minus ln of x squared, and then 1 over x dx. So my 1 over x, I'm just putting out here with the dx so that it matches up with this. So all of this can be replaced with a du. This will be a u, and so now I'm going to have the integral of 1 over the square root of 1 squared minus u squared du. So now that is something that I can integrate. You look back in your math Bible, that is this formula right here. I have a 1 and I have an ln x right here. I no longer have anything out in front of the square root, so initially we thought maybe it was going to be this one, but it ended up being this one. So that's an inverse sine of u over a. Remember that our u is an ln x and our a is a 1. Alright, so the antiderivative of this is Inverse sine of u over a. My u is an ln of x, and my a is a 1, so I don't even have to put that, plus c, and I'm done. And if you'd rather write arc sine instead of to the -1, that's fine as well. And that's your example 2. Example 3. Alright, so on this one, when you look at this, you've got some trigonometry in here. I do have a squared here. This could be written as a 1 squared. But what am I going to do about this sine x? Well, if you let u equal the cosine of x, you're going to need a sine for your du, because the derivative of cosine is negative sine. And so if you switch your signs and then multiply both sides by dx, you're going to have sine x dx can get replaced. Here's your sine x dx. I can give it replaced with a negative du. So now I'm going to have negative du in the place of sine x dx over 1 squared plus u squared, because remember, cosine was equal to u. Alright, so I have a formula for that. I think I used it 2 examples ago. Sure enough, the formula for this was an inverse tangent of u over a, and here we had a 1 over a, which my a value is still a 1. So 1 over a inverse tangent of u over a, and keep in mind that my u is a cosine x, and my a is just a 1, so I don't have to put that 1 underneath here. It's okay if you do. And then normally we would have a plus c, but now I have numbers to plug in. So if I plug numbers into that, I'm going to have inverse tangent of cosine of pi minus inverse tangent of cosine of pi over 2. Okay, now if you think about the cosine of pi, that's a quadrantal angle. Pi's right here. Cosine always references the x value, so the x value when you are at pi is -1. So now I have inverse tangent of -1. Okay, how about at pi over 2? What's the x value when you're at pi over 2? At pi over 2, the x value would be 0. So now I have inverse tangent of 0. Okay, so this one's fairly easy. Where is the slope 0? Because remember this, you're looking for the angle measure that produces a slope of 0. Well, the angle measure that produces a slope of 0 is either 0 degrees or 180 degrees. But remember, when you're doing an inverse tangent problem, you're required to give your answers in the coffee cup handle. So we're going to use the 0 and not the pi. So the answer to that's 0. Okay, now this means where's the slope 1? And tangent has to be negative. So that would be, tangent is negative in these 2 quadrants. But remember, you have to give an answer in the coffee cup handle, so you're going to do a quadrant 4 answer. So a quadrant 4 answer for opposite and adjacent being 1. So if my opposite and my adjacent are being 1, that means we're talking about a 45-degree reference angle. So if you've got a 45-degree reference angle in quadrant 4, you have to give an answer that's between -90 and +90. You can't give one that's just like 315 is not acceptable. It has to be between -90 and +90, but in radians. So you would say negative pi over 4, negative 45 degrees. Negative 45 degrees would be coterminal to positive 315, or 7 pi over 4. So your answer is negative pi over 4 minus 0, which is negative pi over 4. And that was example 3. Alright, example 4. This time we have an arc cosine in the problem, as well as this. So it might be helpful. What was our derivative? The last unit we did was on derivatives of those things. So the derivative of an arc cosine is a -1 over the square root of 1 minus x squared. Okay, well, that's helpful because I think we have that within our problem. All right, so you might think about this problem like inverse cosine of x times 1 over the square root of 1 minus x squared dx. So if you remember right, this happens to be the derivative of this. So this would be a good thing to let my u equal. My u can equal inverse cosine of x, and then my du will equal 1 over the square root of 1 minus x squared. And of course the dx starts out over here, but then we can multiply it over here. And now this is my du. So this problem ends up being a very simple integral. I end up with u du, only I believe this had a negative on it. And that means if I switch my signs, this will have a negative, so I'm going to have a negative out here. And so now my integral is u squared over 2 with a negative. And I would plug numbers in, but I would not plug these numbers in because these are for x, not u. So if I go back and replace my u with an inverse cosine, now I'm ready to plug in the 0 and the 1 over square root 2. So if I plug those in, I'm going to have negative inverse cosine of 1 over the square root of 2 minus negative inverse cosine of 0 over 2. And I forgot the over 2 on this one. Alright, so this means what angle measure will give me an opposite of 1 and a hypotenuse, adjacent of 1 and a hypotenuse of square root 2. That would be the 45. And I'm going to need this to be in quadrant 1 because inverse cosine problems, I have to give answers in the rainbow. And so the positive ones would be here and the negative ones here. So the inverse cosine of this would simply be pi over 4. So now I have a negative pi over 4 over 2. And then these two, of course, can become a plus sign. Inverse cosine of 0. Where is the x value 0 between, or within the rainbow? Within the rainbow, the only place the x value comes out to be 0 is right here at pi over 2. So now I have a pi over 2 over 2. And so if I flip and multiply, I'm going to end up with a negative pi over 8 plus pi over 4, which we should probably do a common denominator for. So common denominator would be 8. So negative pi plus 2 pi is going to end up being pi over 8 for my final answer. So in this problem, we're going to use a little bit of a different strategy. Notice I don't have any squareds in the problem to begin with at all. And to use the inverse trig functions, I'm going to need to have that. So what I'm going to do to incorporate that in is I'm going to say let u equal the square root of x. Because if u is equal to the square root of x, and I square both sides to get rid of this, then I would have u squared equals x. And so then that would allow me, when I go plug back in here, this x could become a u squared, and I would have squareds in my u problem. So let's go ahead and do our du and see if we can make this work. So the derivative of u with respect to x is 1/2 x to the negative 1/2. And let's see, I could multiply both sides by a 2. I'll tell you what, let's before we do that, let's write this a little bit differently. Let's say du over dx is equal to 1 over 2 square root x. Just shoving this thing down to the denominator. And so now if I multiply both sides to get rid of fractions, I have this. And remember, the square root of x we said was equal to a u. Square root of x is a u, so I can replace this with a u. So now I have 2u du in the place of dx. Alright, so if we go back and we plug in our u's and our everything, well, let's see what happens. So that 3 I'm going to push out front. In place of this dx, I'm going to put 2u du. So I'll just put it on top here. 2u du in the place of dx. And then I've got a 2 on the bottom. Remember, the square root of x is equal to u. I can't leave any x's in the problem. And then 1 plus, and instead of x, x would be equal to u squared. So now I've converted this problem from x's to u's, and in so doing that, I've come up with something that will use an inverse trig. These two cancel, the 2 u's. So the 2 u's cancel, and now I've got 3 integral of 1 over 1 plus u squared du. And so I'm pretty sure that's the tangent formula. If you look back in your math Bible, sure enough, that's the inverse tangent integral. And so if you remember from the previous problems, that was 1 over a, so I have the 3, times the 1 over the a value. My a value is just a 1 because that's all I've got there. Plus, or I'm sorry, not plus, but inverse tangent times inverse tangent of u over a, and my u is a square root x. So square root x over a, which is a 1, and then a plus c. So simplified, I just have 3 inverse tangent square root x plus c, and that's all there is to it. The hardest part on this problem is knowing what to do right off the bat. And so kind of the thought process you want to think of is there's no squared in the denominator anywhere. And so in order to make that happen, we let this be u, because I know that when I square both sides, that would give me a squared on my u, and that would help me when I substitute back in. Example 6. Alright, example 6 does have a squared in the bottom, which is great. However, we have 2 terms in the numerator, and that poses a problem, because if you let this be a u, or even the whole thing be a u, your derivative would be a 2x, and we wouldn't know what to do with this plus 3. So what we're going to do is we're going to separate that into 2 separate integrals. We're going to say, hey, we've got the integral of 4x over 1 minus x squared dx plus the integral of 3 over 1 minus x squared and a square root dx. So just separating it into 2 separate problems, since they have the same denominator, we can do that. And so now I have 2 separate problems. This problem is pretty much like one of our previous examples. This problem is going to be like one of those from back in early in chapter 5, where we said let u equal this entire denominator, because the derivative of this denominator is contained in my numerator. So we kind of want to work these as 2 separate problems. So the first one, we're going to say let u equal 1 minus x squared. And then the derivative of u with respect to x will be negative 2x. And so that means I would have a negative 1/2 du equaling a x dx. So x dx is going to be negative 1/2 du. So if I plug back in there, I'm going to put that 4 out front. Then I have an x dx here. So the x dx is this. So I have a negative 1/2 du over the square root of u, because this is my u right here. So that would be u to the 1/2 power. Alright, so the negative 1/2 can pull completely out to the front. So if you take 4 times a negative half, that's negative 2. And so I have negative 2 integral. You could shove this up to the numerator and make it u to the negative 1/2 du. And then I would just use the backwards power rule, add 1 and divide by that number. So if I add 1 to this, I get a positive half. So I have negative 2 u to the positive half divided by a half plus c. And I can ignore that plus c for now because I have 2 terms. And so now if I plug my x values back in, that one is going to come out to be, let me shrink this one up just a little bit so that I've got room down here at the bottom. So I'm going to flip this 2 up and multiply it times this one, so it becomes a negative 4. So I'm going to have a negative 4, and then my u value is a 1 minus x squared. Square root of 1 minus x squared. Flip that over, plug in for u, 1 minus x squared, and so that is my integration for the first part of this problem. This one, I'm going to go back to my math Bible, and you do have a formula. It's inverse cosine. Inverse cosine is when you have a square root with a 1 minus x squared. So to do this one, I can pull my 3 out front, and I don't even need a u because it looks just like the one in the math Bible other than a negative. So I can adjust that negative. So if you look back at the formula in the math Bible, this is the formula for integrating an inverse sine problem, not cosine problem, but inverse sine. This is my a. If I make a 1 squared, and this will be my u. So I'm going to have 3 inverse sine of u over a, and my u is an x and my a is a 1, and so that is my second term. It was actually a little bit easier to work than the first one. Now I can put my plus c on, and here is my answer. So kind of 2 problems within one almost for example 6. Alright, so example 7, and this one is an example of where completing the square is going to help us on this one, because I do have the square root. I have a squared in here, but it's this x that's throwing me off. So if I can do a complete the square to get a binomial, that would be helpful here. So the process of completing the square, we can kind of do that over to the side here. I have the x squared minus 2x. To complete that square, I'd want to take half of this number, half of 2, and you don't have to worry about the negative because you're going to end up squaring it anyway. Half of 2 is 1, and 1 squared is 1. Remember, you take half of this number and then square it. So half of 2 is 1, square that, I'm going to get a plus 1. So to counteract a plus 1, I have to do a minus 1. Now this will factor into a binomial squared. In other words, if you want to write it like this, you can. What multiplies to give me 1 and adds to give me negative 2, I would need x minus 1 for both. So I have x minus 1 squared, and then I still have this minus 1 over here on the end. So I took what I had in here, I started off with that here, I added and subtracted a 1, so I didn't change the value any, and now I've ended up with this. So I can replace this with this. All right, so now if you go to your math Bible and look at the very bottom right, there is a integration for inverse secant. And if it has a u here, and then a u squared here, and then an a squared here. So if I put a little squared on my 1, my a value once again is going to be a 1, and this is going to be my u right here. So our u is going to equal x minus 1, and the derivative of that is just 1, so I can go directly to the formula. There's no adjustments that need to be made with my u. So if I integrate, the formula says, here's the formula, I'll just write it down, 1 over a inverse secant of u over a plus c. So if I integrate this using that, this is my u, and my a is a 1. So I'm going to have 1 over 1 inverse secant of u, which is x minus 1, over a plus c. And so to simplify, I have inverse secant of x minus 1 plus c. All right, and then one more example. And so this is another one where we can complete the square. Obviously, I have a square, even have a 4th power there. But there is nothing that will multiply to give me a positive 9 and add to give me a positive 8. Unfortunately, I would be able to subtract, but I can't add to get those, so that's not going to factor. So if I were to complete the square over here to the side, negative x to the 4th plus 8x squared plus 9, I'm just reordering it. Remember that when I complete the square, I need this to be a positive, so I'm going to factor that out. So that's x to the 4th minus 8x squared. I'll leave the 9 out here, because I would have to put it out there anyway. And I know these are bigger powers than we're used to, but it still works the same. If you have a squared, and then if you were to let u equal x squared, we could do that. But we'll just leave the squareds in there at this time. So half of 8. Half of 8 is 4, and 4 squared is 16. So if I want to complete the square, I need to add a 16 to this problem and subtract. Let me move this over just a little bit so I have more room. So I want to add a 16 and subtract a 16, and I still have my plus 9. So the black is what we had before. I've added in a plus 16 and a minus 16 inside of this parentheses, and I got the 16 from taking half of 8, which is 4, and then squaring it. In order to factor, I just need these 3 to factor. So this negative 16 is multiplied times a negative, so out here it would be a positive 16. So now I have a negative sign, x to the 4th, minus 8x squared, plus 16, and then I have a plus 16 out here as well, because this one is multiplied times that. Alright, so now we can factor this down to 2 parentheses. So if I factor that, that would be a 25. And this one, if you factor that, you're going to have an x squared and an x squared here. Well, multiplies to give me 16 and adds to give me negative 8 would be negative 4. Whoops, I don't need an x on that. A negative 4 in both. And so then that is x squared minus 4 squared plus 25. And I could reverse that order and make that 25 minus x squared minus 4 quantity squared. So I have taken this thing that was right here from here and transformed it into this. Something that I have, this could be my u, and this could be my a. So if I rewrite this over here, we will have an x on top and the square root of 25 minus x squared minus 4. Alright, so to save room here, I'm going to get rid of some of my completing the square work, which you could always rewind the video if you need to see it again. Alright, so this is an x squared. Let me erase that, make it a little nicer. Okay, so now I have the square root of a, and you could think about the 25 as a 5 squared, where a is a 5, and this is going to line up with the inverse sine formula. So I'll think about this as being my u. So if u is equal to x squared minus 4, that means the derivative of u with respect to x would be 2x. And so if I divide by 2, I get a half du equals x dx. So I can replace this x dx with a 1/2 du. So I'll put the 1/2 out in front. There's my du. And then I have the square root of, we'll say 5 squared instead of 25, so we can see our a value, minus u squared. And I forgot that squared right there. Alright, so now I can use my inverse sine integration formula, because it says a squared minus u squared, and that integration is inverse sine of u over a. And my u is x squared minus 4, my a is a 5, and I had a 1/2 out front, and then I would have to put a plus c on that. And then that is your answer. Alright, and that's your last example. Homework will be posted in Schoology.